Well, welcome everybody. It's great to see many of you guys again. If only virtually. I definitely hope to be doing this again in person in the near future. I also wanted to just start off by thanking you all for all the time that many of you have spent with us over the years. I know that most of you are well familiar with the Pure story and portfolio, and certainly your time is valuable. So knowing that, we've prepared a great set of really meaty topics to tee up today. Before we kind of dive into the details, I just wanted to share a few words on the overall portfolio here at Pure, as you know, comprised of FlashArray, FlashBlade, and now the Portworx product line, and some of the larger trends that we're investing toward really across the company. And for me, that really breaks down to three things. One is expanding our as a service offerings, building on kind of our Evergreen subscription and model into a full as a service experience for our customers across the portfolio. Number two is focusing on the needs of modern applications, and whether that's cloud native or container based applications, or fast object storage, or just tying it all together. And number three is and this is where we'll spend the majority of the time today, is really continuing to lead the way in innovating in the Flash and core platform technologies. And so with that in mind, we wanted to spend the majority of the time today really focused on FlashBlade, which, as you'll see, blends a lot of the elements and themes that I just touched upon across the portfolio. So to lead us off in kind of diving into FlashBlade, I'd like to introduce Matt Burr and Rajiv Rajaswamy, sorry, the GM, their general manager of FlashBlade, and our VP of product management for FlashBlade, to help set the stage with FlashBlade and where we're at as a business. And I'll be back in a little bit to do a little bit of a deeper dive into the product and architecture. So Matt, Rajiv.
Thanks, Rob. Hi, everybody. I echo Rob's thanks and sentiment for spending some time with us. We appreciate it. As Rob mentioned, I'm Matt Burr. I'm the general manager of the FlashBlade business unit. You'll notice I do not have an orange background. This is my own personal rage against the machine of COVID. I have only kept my kids' art up behind me, as opposed to ever using a virtual background. So I appreciate the fact that nobody even bothers to try and ask me anymore. Once COVID is over, I'll start using virtual backgrounds, but until then, it's my kids' art. I've been with Pure since 2010. I'm employee number 11 here. So I have had a front seat to this company's journey, and also have a tremendous amount of pride around the things that we've engineered. One thing that I'll note that Rob touched on is, we oftentimes, or it's often misconstrued that Evergreen is a subscription or a business program. And while it is that, it is actually more an engineering philosophy than it is a business program. It is what allows us to get to subscription. It's one of the drivers of a tremendously high NPS score inside of our business. But ultimately, at its core, it's a strive towards modularity in our products that allows us to do things that other companies can't do. Upgrade components in place, have systems that, get bigger capacity-wise, but smaller footprint-wise. And we'll dive into some of the benefits of that in the FlashBlade architecture. So I just wanted to do a quick introduction. I will pass it over to Rajiv. I will be here the whole time. Unfortunately, I'm someone who can't keep my mouth shut, so you will probably see me chiming in or hear me chiming in at different times, both during Rob and Rajiv's pieces. So again, thank you. And it is Rajiv Rajaswamy. He has been here for quite a long time. I could give you his phone number. I know it by heart. It's the only one I know besides my wife's. So Rajiv, over to you.
Thank you, Matt. Like Matt said, my name is Rajiv, and I'm a VP of Product Management for FlashBlade. I've been at Pure for close to 5.5 years. And before Rob dives into the meat of the presentation, which is the architecture of the product and the architectural details, et cetera, I was going to take a few minutes up front to give you guys a sense of where how FlashBlade is doing, where it's being deployed, what kind of use cases, and also kind of teed up for Rob by kind of talking to you guys about it a little bit about the early decisions we had to make, which shaped the product the way it is, And obviously, Rob's going to go into a lot of detail around that. So with that, let me share my slides, and please let me know once you see this. So let me start out by, I'm sure you guys have seen slides like this before, but the reason we put this up is to sort of let you know that Rob mentioned that they started basically noodling on the idea of FlashBlade back in 2014. And when Rob and team were designing the product, our goal was to focus on modern unstructured data. And we contrast that with traditional unstructured data on the left-hand side. So given that we wanted to focus on what you see on the right-hand side, there were a certain set of design decisions that were driven by where we wanted to focus. So if you look at traditional data, like with workloads like file sharing, user home directories, user shares, etc., those tend to be horizontal, and usually IT departments own that kind of data. And essentially, those are not specific to any vertical as such. So in contrast, if you look at what we call modern unstructured data, while there are a few horizontal applications like log analytics, for example, like Splunk or Elastic, etc., a lot of these applications and the data generated by these applications tend to be industry specific, vertical specific, etc. So we had to make sure that the systems, the storage systems we were building, were going to be super simple to use. There's not going to be storage specialists. Oftentimes, people in the lines of business own and operate these systems. So simplicity was very high on the priority list for us. Also, in terms of scale, if you look at traditional data versus modern unstructured data, the scale and size of the data is order of magnitudes more. So we need to make sure that the system was scalable from tens of terabytes to petabytes. And we made a big bet early on that a lot of the modern unstructured data is going to need very high performance, even at scale. So, and the second big bet we made was that object, which at that time was mainly used for archive and cheap and deep storage, was going to be deployed more and more in high performance applications. And the other decision we had to make was, there were vendors in the past that have focused on a niche, especially for scale out unstructured storage, like for example, oil and gas or media entertainment. We made an early decision to build a system that would address a broad swath of unstructured modern applications. So in hindsight, a lot of, if not all of those decisions have paid off really well for us. And over the next couple of slides, I'll walk you through the success we've had, make the success tangible, and show you where we're being successful. These are basically business metrics, and these are a sample of the business metrics, if you will. We are well over $1 billion in cumulative revenue to date. We haven't announced our earnings yet, so that number will only get bigger. And we've shipped well over an exabyte of capacity. Matt, you wanted to say something?
How did you know that?
I saw you come off of mute.
Oh, wow. I thought you were reading my mind. Yeah, so I don't, I want to underscore this point of, over $1 billion exabyte of capacity, kind of while maintaining this, 85.2 net promoter score. Look, I'm a big believer in, the differentiation is always in architecture. And, why you built what you built is oftentimes more important than what you built. But the whole circle of life of that relationship is predicated upon having successful customers. And in order to have successful customers, you also have to have a business that can scale to support these kinds of numbers. And so, I'll start with the exabyte of capacity, right? You have to have a supply chain to be able to deliver, supporting, over, $1 billion in sales. And this was, last year we raced through that mark, and still maintain, a net promoter score, in this range, requires a pretty hefty investment in supporting those customers. So, the point here is that as this space evolves, and when I say this space, I mean unstructured data, and what I mean by that is the evolution of disk to flash, excuse me, in file and object. There will be new players in this space, and the reality is, we've got a big jump on being able to scale, to continue to scale our business, on and into a $1 billion run rate. So, the numbers are great when we look at them and say, boy, that's interesting. There's a lot of milestones achieved there. The reality is the biggest milestone achieved is being able to maintain success through that growth.
Thank you, Matt. The other set of
I got a question on that note, as well as the other chart. When FlashBlade first came out, you were looking at lots of markets, and then kind of regrouped and targeted, in our understanding, the data protection space, because that was the one space that was really adopting the object storage early on, 2017, 2018. Can you talk about what that 1 billion looks like now today in your 200 customers? So understanding what that shift has been over the last maybe 3 years, since the performance has become more interesting to the market.
Yeah, it's a great question, Kimberly. Okay, so just to clarify one thing, the 200 customers, that's about 200 customers with more than $1 million in FlashBlade sales. So we have well more than 200 customers in total. Your observation is correct that when we launched FlashBlade, it launched at a broader market that for any number of reasons, primarily price point, but others just feature maturity, wasn't going to be a broad horizontal play into unstructured data, right? We were not looking at things like file shares. We were not looking at, traditional file and object workloads. We were not looking at general purpose NAS. We were looking at things, kind of up the stack in terms of, early Splunk deployments and, really heavy HPC environments where, due to the architectures of existing products, you had these sort of pod architectures that were small and required these management frameworks to manage. You had many pods of, you could, in some instances with some, customers in the chip design space, you would have hundreds of these pods, which, were the only way you could get the work done, but they were very difficult to manage. What we have is a very highly scalable metadata platform. And that allows us to basically consolidate areas that have previously been distributed in customer environments. So your observation on data protection, there's a little bit of what I call unfortunate luck or unfortunate timing for us. The emergence of ransomware came around right when we were beginning to realize that we had customers that were using our system for data protection. It actually came up in an EBC, and we were in the EBC, and the customer said, "Look, anybody can sell me backup. What you've sold me is recovery." And there was this inflection point in kind of 2018, 2017-ish, when even disk-based backups or disk-based restores were too slow for some primary workloads. And so that's where we saw sort of Flash make its entry point into this space. Since then, our use cases have broadened out to include traditional HPC, chip design and EDA, analytics in terms of Splunk and sort of the modern SIEM type analytics, as well as in healthcare. So we shipped SMB a little over a year ago, or right around a year ago, and SMB has allowed us to get into the healthcare space, for example, with PACS applications. And if you're in the specifics of a PACS environment, right, typically what happens is you have all of this ingest that comes in, and generally there's ingest and then there's render. And so you ingest everything, the images get rendered, and then you can start looking at them, and there's this big delay. we've found that with, our big sort of research oriented customers, which we have a slide on this in a second, the render of the first image is actually completed before, a tenth of the ingest has even started. So what that allows is for the researchers to begin looking at results sooner, and they can see results faster. So, it's a great question. Yes, data protection was kind of the spearhead, also a bit strategic, by the way, but, one that has now broadened out into multiple use cases. Does that answer your question?
I guess I was actually trying to figure out on your, let's say 200 customers or the 1 exabyte shipped, what percentage of that is data protection, and what percentage of that may be other applications?
We'll touch on that. It'll become more clear in a couple of the next slides.
Thank you, Matt. So I'm gonna get to the, by the way, I just wanted to sort of point out, I think Matt already mentioned this, that the approximately 200 customers you see here are customers who've bought more than $1 million worth of FlashBlades. We have a lot more customers than 200, just as an FYI. Just in FY21, which is calendar year, for the most part, calendar year 20, we added 300 customers. So you could kind of basically guess at the scale. Obviously, we are proud of the awards and recognitions we get, and just both from analysts as well as customers, as represented by the leadership in the Gartner Magic Quadrant that came out last year, and the GigaOM for performance object, and also the Gartner Peer Insights, which is essentially mostly made up of customer testimonials. This is just a sampling of the awards we've gotten. But to get to your question, Kimberly, this represents a snapshot and a sampling of how customers are using FlashBlade and where FlashBlade is deployed. If you kind of look at the categories here, geographically, we have a presence in nearly 40 countries. And outside of the US, more than the government agencies of more than 10 countries have deployed FlashBlade. That is geographically speaking. And the data protection part that you talked about is on the top left-hand box, which is primarily used for recovery, fast recovery. And as Matt mentioned, right, this ransomware has given us a little bit more of a boost in that area. But what you'll also see is that we are deployed in really large enterprises, as represented by 4 of the top 7 trillion-dollar-plus companies, the 3 of the largest US banks, and the 5 of the top semiconductor companies. And all of these are really large enterprises. And that is the large enterprise sector. And I personally am basically really stoked about what we call the leading edge applications, like autonomous vehicles, cancer research, space exploration. And when we talk about semiconductors, autonomous vehicles, even banks for that matter, they're not deploying this only for data protection. For example, in the banks, they use FlashBlade in quant analysis. The autonomous vehicles, they're using us for software development. And Matt already mentioned about PACS. We are also deployed in genomics for sequencing. So what customers consider, there is a general association of unstructured data with secondary data, which today is not the case anymore. I mean, for cancer research, or for genomics companies, sequencing is what they do. That's their primary workload. And FlashBlade is deployed in a lot of these customers to address their mission critical primary workloads. It just happens that they're not OLTP databases or VMware or VDI kind of workloads, which are more block oriented. So just wanted to make sure that we kind of made that clear. Rob, did you want to say something there?
Yeah, no, and Kimberly, just wanted to come back to your question here. And, I think what you'll see is you'll find some customers in multiple of these boxes, right? So for example, we have large bank customers that started with us as a rapid restore, backup target and rapid restore source, and are using FlashBlade for that by night, but by day are using the same FlashBlade and same set of assets to power machine learning and AI training, right? So what we've found is that our ability, and we'll get into this in more detail about how we've built this, but our ability to serve multiple workloads, to be able to serve them simultaneously, is driving a new wave of consolidation in how customers in the unstructured data space are thinking about combining what have historically been fairly siloed and disparate workloads onto the same set of assets.
Yeah, and there's one box here that I'd like to point out, is that a second box from the top on the right, horizontally going. So it is the 70 billion plus objects. We talked about scale. We actually have software development companies with relatively small sized FlashBlade systems that are running 70 billion plus objects without sacrificing any performance there. When we talk about scale, we're not just talking about the single namespace that we're able to provide with a single cluster, but within that namespace, how are you able to scale your objects, your files, file systems, etc. So there is and Rob's going to go into the details of this. And so you could see what leading edge customers are pushing in terms of scale, especially with objects. And that system is not sweating at all with 70 billion plus objects in it. This is just, we talked about general areas where FlashBlade is deployed in the previous slide. This is a set of referenceable customers, and it gives you a sense of the different industries and the diverse industries where FlashBlade is deployed. These are all public references for us. As an example, again, just to drive the point home that it's not just backup. The Mercedes Formula One racing group uses us for design and simulation. They do it using computational fluid dynamics. The data set that's gathered and all the modeling they need to do for simulation and design of race cars, etc., is where FlashBlade is deployed. So just to give you a sense of how FlashBlade is being deployed above and beyond the data protection. So with that, I will turn this over to Rob. Rob, I'm gonna stop sharing so you can drive. And if any questions come up, I can answer in chat.
Sounds good. Let's see. All right, is that coming through for everyone?
Yep.
Yes, absolutely. We can see it very well. Thank you.
Awesome, great. Well, so for this next section, I wanted to focus on diving into a couple aspects of the FlashBlade architecture that uniquely set us up to deliver on some of the results and really across the different sets of verticals and use cases that Rajiv just outlined. So, all right, now I got to figure out how to advance these slides. There we go. So, before I dive in to some of the product architecture, just a quick reminder of basic product overview and form factor. As you know, FlashBlade is built on a bladed chassis design, and we're capable of scaling out from under a single chassis to over 10 chassis. We ship multiple blade sizes, 17 terabyte, 52 terabyte blades. And so the way to think about this is we have the ability to help customers scale out by adding more blades, as well as scale out capacity by moving to larger blades, and any combination kind of in between. To just kind of orient this to some concrete numbers, our systems will grow anywhere from a couple dozen terabytes up to over about a petabyte in effective capacity. On the performance side, certainly, designed, as Rajiv said, to be capable of very high performance. But, I would say just as importantly, we focused in, our philosophy in design and architecture on delivering predictable and linear scaling performance, right? We knew up front that, customers were going to start with us, wherever they started, potentially at a small, size and scale, and grow continuously throughout their lifetime. And what we wanted to do was be able to provide them a very predictable and linear way to scale their performance as they grew. And we'll get into some of the details, hardware and software, about how we enable that. And the last point I just want to touch on in terms of a platform overview is the integrated networking. This was a very kind of key decision early on we made, really to drive simplicity. And the I would say the critical observation we made is that historically scale out and distributed file systems had really, in some sense, punted one of the hardest problems in scale-out systems over to the customer, which was networking it all together, right? Storage vendors had historically, I would say, stopped at the water's edge, provided the storage, but said, hey, Mr. Customer, we'll leave the networking as an exercise to you. And if you actually look at where a lot of the complexity and reliability issues come in, it has been in that networking layer. And so what we decided to do from very early stage was take on that complexity ourselves, build that networking layer integrated into the product. And by doing so, not only provides simplicity, but as you'll see in the next half hour or so, really help us drive a considerable amount of performance and a lot of the key product attributes that we built the software around. Quick look back at the last 6 years of continued innovation as we started off the session by doing a quick poll. We launched the product in 2016. Since then, a huge number of follow-on additions, everything from expanded blade options, going from initially 8 terabyte blades, 17 terabytes, 52 terabytes, dramatic expansion in scale. So really growing out from our single chassis, up to 15 blades, growing that by 10x up to 10 chassis or 150 blades. Dramatic expansion in protocols. When we launched the product, we were really solely focused on NFS v3. You fast forward, 5-6 years, and we have customers with NFS v3, NFS v4, SMB, Object. All of those are very significant adoption and growth areas for us. Data protection, so whether that's snapshots, whether that's immutable safe mode snapshots, whether it's replication capabilities, whether it's replication capabilities to the cloud, considerable number of features that we've added there, as well as just a general set of what we would consider enterprise integration or capabilities. So these are things like quota management, security integrations, management monitoring, audit logs, all the things that all the things that enterprise IT teams need to really deliver to their customers on the promise that Rajiv mentioned, which was how do you give non-technical users, whether they're AI data scientists, whether they're fluid dynamics specialists, how do you give them access to high performance storage without requiring them to be storage experts? So again, a lot of stuff here, not going to unpack it all, but really the takeaway point here is the last 6 years have been just a continuous march of add-on innovation, a ton of added capabilities. And most importantly, getting back to that Evergreen philosophy, which Matt expanded on in the beginning, most importantly, all of these delivered non-disruptively with zero planned downtime. And that really is, at the end of the day, a key part of our philosophy and promise to customers. So, So what allows us to do this is really the layering of the architecture that we've built in FlashBlade. From the bottom up, we've got platform layer, integrated hardware and software that really provides the basis of everything we do. We build upon that a core set of data services, which we'll spend a tremendous amount of time kind of diving into how this works. And then at the top of the stack, are all the data services that we just talked about, whether that's the protocols, file, object, the data protection features, security quotas, all the enterprise capabilities that we discussed.
Robert?
Yes.
Yeah, you show a lot of features which are impressive, but you have also a lot of competition. Can you name 2 or 3 features that make you unique, better than the rest?
Well, I can name certainly more than 2 or 3 if I had to pick 2 or 3. But if I had to pick 2 or 3, I would say, I would start with how we deliver those features, right? Getting back to Evergreen, getting back to our, our ability to let a customer evolve from a very early or small stage and grow in performance, scale, capacity, all non-disruptively, to take all of that set of features of the last 6 years, through continuous non-disruptive upgrades, and we'll provide a couple examples of customers that have been through that journey with us. I think that's number one at the top of my list of things that set us apart. Number two, I would say, is really the performance that underlies a lot of the mixed protocol and mixed workload usage, right? And we'll spend a bit of time talking about the underpinnings in that core services layer I have on this slide as to what allows that. But more simply, I think one of the things that really sets us apart is customers are able to put any number of and variety of unstructured data workloads, whether it's file, whether it's object, on FlashBlade, without having to worry about disparate performance, without having to worry about, hey, is this application, the fact that it works with small files and this other application works with large streaming sequential data access and this other application works with object storage, can these all coexist on the same asset without interfering with one another? That's something that really sets us apart. And then, I would say that, getting back to the, I would say discrete feature category, I would say that, our data protection stack and particularly safe mode snapshots is something that really sets us apart. Our ability to build on our core metadata, the technology that we've built to provide essentially zero cost snapshots, and then further secure those and essentially vault them for customers and help customers secure those online snapshots, if you will, from potential intrusions or ransomware attacks is something that sets us apart. And I think that's something that is a bit unique. I think historically there's been a bit of a false dichotomy, a trade-off that customers have to go through between, hey, do I want to take a bunch of snapshots and potentially impact my production performance, or do I want to optimize for production performance at potentially the risk of data protection? And we've essentially removed that dichotomy and changed that equation. So for me, those would be the top three, but it's actually a really good question. Matt, what would you say?
Okay.
Yeah, so what I was going to add to that is, features are generally, and I know it's going to sound odd, but features are generally backward looking because you're building something to, meet something that exists in the market. We look to actually minimize the number of features that customers need through architecture. And so, for us, architectural differentiation, I think, matters significantly. If you look at the industry today, for example, some of the newer entrants in the market are relying on an Optane tier or storage class memory, right? SCM is fundamentally more expensive than some of the most expensive components of the system. Our ability to have scalable metadata engineered into the core of the program, core of the project, or product, is a architectural feature advantage that is unique to us. So there are other examples like that, not having to use Q trees, for example, or structures of data in that way. But what allows us to differentiate is really at the core of the product and the architecture. The features themselves, are somewhat table stakes.
So jumping back in, again, just wanted to set the stage with really the three architectural layers that we've built in FlashBlade, and we'll be kind of diving into each of these, whether it's the top of the stack, the core data services, the metadata engine, and kind of the core processing engine that supports a lot of the architectural capabilities that Matt just touched on, or the underlying integrated hardware software platform layer. Before we go any, before we kind of dive deeper, I thought it'd be interesting to step back and just take a quick look at how this all comes together in a live system. And we'll see, I've been told that this group likes live demos, so we'll see if we can accommodate. This is what I've done here is logged into essentially the monitoring GUI for one of our live test systems internally. And this is running pre-release software. And this is a test system that's used for a variety of different purposes. It's one of our larger test system. It's 5 chassis in size. You can see kind of the hardware view off to the right here. The 5 boxes in the bottom represent each of the chassis, and then you've got the 15 blades within each of those chassis. and then a set of networking switches, effectively kind of external fabric modules up at the top. And so what this test system is, doing is among a number of other things is running one of the largest internal engineering workloads we have here within FlashBlade, which is our internal analytics pipeline. And this is a pipeline that is analyzing tens of thousands, I think it's actually over 40,000 test results daily. What it's attempting to do is look at each of the test runs, the logs that are coming out of those runs, and automatically detect and triage patterns and problems to flag to engineers. So for example, if engineers check in something that creates an anomaly, a test failure, some sort of condition that needs to be looked at in the logs, that might show up in 1,000 different test runs. How do we prevent 1,000 different engineers from being assigned to work on the same issue? There's an incredible stack of essentially analytics that we've built up to parse those logs, apply models, and apply essentially rules to automatically triage that. That all comes together on this system. In addition to that, there's any number of ad hoc testing, that's being done in the system by software developers. So, quick dive in, what you're looking at here is kind of the dashboard view. You can see it's, this is right now providing a little bit over about a couple petabytes of storage, but spread between file systems, object stores, as well as data protection snapshots. On the bottom here, you can see kind of the overview, system level overview of performance, whether that's latency, IOPS, bandwidth. We can dive into, if we dive into a little bit more the detail on the performance, what you can see is, we've got a mix of usage, whether it's file system usage. Let's see. Here we go. Sorry. See, this is the problem with live demos. So what you can see here with the performance kind of drill down is if you separate it out by protocol, right? We've got a fair deal of file system access that's happening over HTTP, NFS, and S3, and we can help users kind of segment out where the performance drivers are coming in. So whether it's HTTP driving, and I think we can go down to 5-minute granularity here, whether it's HTTP driving bursty spikes of reads and writes. And this, obviously would be expected. This is where, some of the log ingest and, transitions in the pipeline are happening over HTTP. Whether it's the majority of the data access and processing that's happening over NFS. And so this is where you see a much, still very bursty overall, but much higher general sustained workload. Or on the object side, which when I checked in the system last night was running, and it doesn't look like there's much activity right now. Like I said, there's quite a bit of usage on this system. If you if we dive into looking at kind of where the storage breaks up, you can see on the file system side, we've got a number of different file systems set up. If we sort them by overall essentially capacity usage, you can see that the largest file system by far is this one at the top, and that's really the dumping ground, if you will, of all the logs that are coming from all of our testbed systems. So that's where all the logs get essentially ingested and planted into the system. From there, there's really a sequence of different tools that we use, whether it's Kafka, whether it's Spark, whether it's Elastic indexing all of these logs. That take the raw logs, generate events that eventually generate essentially automated tickets for engineers to look at. And so what you can see here is really a breakdown of the different file systems that each of those tools or each of those stages of the pipeline use, whether it's the at the top, the raw dumping ground. I believe the second file system is used by Elastic for its index. You can see the Kafka file system below. We also have syslog, our syslog processing that happens at an early stage of the pipeline. So you can see again, each of the different applications carving off space on the same FlashBlade for this purpose. Same thing on the object store side. I think this is where you see a bit more of a mix of ad hoc testing. We've got Spark usage. We've got I think the largest bucket we have here is being used as essentially an artifact repository. So all of the artifacts that get built in our build system end up here, and then this becomes kind of the distribution point for those artifacts. So really the takeaway point here is this is a great example of how we internally, as well as our customers, are using FlashBlade to provide shared storage for a variety of different applications, and oftentimes applications that have very different performance needs, very different I/O patterns, and are operating in tight concert with one another, right? Each stage of this analytics pipeline is essentially taking in data from the previous stage, doing some processing, writing out intermediate results, signaling an event, and then handing off that kind of process data or process results to the next stage in the pipeline, the next application set. The last thing I want to share about this environment and kind of how it's evolved over time is, this is an environment that was really conceived to grow with our engineering team and grow with our engineering effort as we built FlashBlade. And so if you think about it, in the early days, we had a couple dozen engineers, a handful of test systems, a couple hundred to 1,000 tests. We've grown each of those by either 10x, 100x, even 1,000x. And so as we've grown the system, different stages of the pipeline needed to grow in different proportions. As we grew the number of test systems, we had more logs being ingested at the front door, but the number of unique failures or signatures or fingerprints grows more with the scale of the number of unique tests or the number of unique changes that are coming into the system. And what that means is that if you look at that pipeline and describe whether it's Kafka, Spark, Elastic, syslog, or custom software processing, as we grow and scale, different elements in different applications have to grow in different rates. And so what FlashBlade has been really good at is essentially providing the ability to scale the application set in different proportions without having to make changes to the storage infrastructure. Right. So as we needed to, for example, double the number of Spark nodes, we didn't have to change anything at the storage layer. And this is a great example of how what our customers are finding as well. So let's switch back to the slides here. And I want to dive into now a lot of the kind of architecture details and fundamentals of how this all fits together. All right, so let's dive in. A quick look at what we mean by data services. If we start at the top of the stack, so first and foremost, we discussed before, wide range of file protocols, whether it's starting with NFS v3, NFS v4 now, SMB, as well as object storage. And what we've seen over time is customers are really making, very, I would say, blended use of all these protocols. We have customers that start with NFS and then grow into object. We have customers that start with object, grow into file, but we do see a great number of customers, I would say the majority of customers, using multiple protocols and multiple protocols simultaneously. In addition to the namespace protocols and access protocols, we certainly have management monitoring APIs. It doesn't do much good to provide a ton of performance if you can't, see where it's going and stay ahead of potential bottlenecks and issues. And then below kind of management and data access APIs, you've also got data protection, right? Snapshots, replication. We talked about safe mode snapshots. This is something that we've really been able to build on. Our snapshot technology and our ability to provide customers rapid restore, and provide some additional security capabilities to essentially let customers take a snapshot and hold it on the array with full confidence that even if their environment is compromised, even if the array somehow access to the array is somehow compromised through credentials or whatnot, that the snapshot is still immutable, right? That snapshot can't be removed and could be restored to very quickly. So, like I mentioned before, a whole host of enterprise feature capabilities. A great example of kind of the need, I would say, for these feature capabilities in combination, in concert with high performance is in the chip design or kind of the broader space of technical computing, right? I think if we look at chip design, for example, undeniably, these are environments that need high performance, that benefit a great deal from a huge degree and scale of performance. But they're also a great mix of different types of performance needs, right? You've got massively complex, environments, a combination of different pieces of software, whether it's, front-end design, whether it's back-end synthesis, validation with firmware, compiling, compilers and tool chains, operating systems. You've got tens of thousands of engineers that you're supporting, often working globally. These are 24/7, systems, and they're often driven by massive compute clusters, right? We're talking, tens of thousands of cores. And so when you think about the systems at this scale, they really are full-on 24/7 live production systems. And with that lens, right, you have to think about, well, what are you going to do if there's a runaway job? What are you going to do if there's a configuration error, human error, a failure in the network? How do you prevent that from stalling the entire, pipeline and generating a huge, essentially production outage? This isn't just theoretical, right? This is a Pure One dashboard from one of really the largest global semiconductor companies. And, really what you see here is, what I just described. It's a large grid environment. I believe this is, thousands of users. I think it's tens of thousands of compute cores running all of the mix of workloads I just described, whether it's verification, synthesis, or place and route jobs for future designs. And as we expect, not only are they driving a great deal of performance, but this particular customer is, also using all of our data protection capabilities, whether it's snapshot policies, replication, really the whole 9 yards. So let's dive into kind of the layer below this, which is really what allows us, enables us to build all these enterprise features on top of. If we look back at when we started FlashBlade, Pure kind of announced Flash for all. This was, our idea that we could make Flash ubiquitous and really a ubiquitous replacement for disk. Fast forward to today, we really think about performance for all types of workloads and across all types of industries, which Rajiv kind of touched on. I think the biggest thing that we've learned, since we started FlashBlade is that, performance comes in all shapes and sizes, and certainly it's the low latency, high throughput, access, as well as high metadata performance. But it's also the ability to serve large files. Large smiles. We do like to deliver large smiles as well. Large files, small files, a variety of different types of access, whether it's random or sequential access. And I'd say more and more it's a combination of all those things at the same time, right? As we looked at our internal system, we looked at the EDA systems. I think those are great examples of all of those elements coming together. And so if you look at what we're designing for, we want to design for large scale, certainly cost efficiency and performance. What does that drive us to? Well, it drives us pretty quickly to, needing a scale-out architecture. We need this to cover kind of the 100 to 1000x range of scale we want to build to. We need to design an architecture that's going to allow us to be able to drive linear scale and performance without introducing bottlenecks. Historically, this has been one of the biggest limiters of scale-out systems is, how far can you scale before the performance bottlenecks creep in? And we need to design for a wide range of media, to deliver on the Evergreen promise and really, play for the long term. We want to design for what's there today, but also what's coming ahead, as far as the media roadmaps. And so, let's start with a kind of the core scale-out architecture and what drives that. I would say at the heart of it, we approached this issue, right? The kind of core scale-out architecture engine. We approach this very differently than many others in the industry have historically, as well as since we launched. We really took our cues from the parallel database community. We took three basic key ideas and used them to build the core engine of FlashBlade around it. And I want to spend a lot of time walking you guys through this. Those three core ideas, number one, right, was to really flatten the representation of everything that we store in the system, whether it's data or metadata, but really change how you would typically represent things like metadata, flatten it to look more like a database table, if you will, and really make it easier to partition and shard up. Number two is, once we've done that, is to focus all of our efforts on being able to parallelize everything across the system, whether that's access and data path, in terms of I/O, whether it's access and control of metadata, whether it's serving user requests, whether it's driving background jobs like garbage collection or flash management. We want everything in the system to be as parallel as possible. And then number three is, optimize for the coordination of the changes that you do have to manage, right? So this idea of parallelizing everything into autonomous independent pieces is great, but at the end of the day, you do have to kind of coordinate those pieces. We want to optimize that coordination. And so, more simply at a high level, right, we recognized early on the way that we were going to avoid bottlenecks was break the problem into as many smaller pieces as we can, enable as many of the compute cores in the system to be targeted at those small pieces of the problem as we could, and then minimize the cost of piecing it all back together, right, coordinating that work. So, let's unpack some of that a little bit and talk about how, what that actually looks like. So let me start at the top, right? So, I said kind of key idea number one was to flatten the representation of everything that we store in the system, data or metadata. And so, what we do there is essentially we collapse and represent all the metadata in our system into what looks very much like a key value database representation. This is in contrast to, perhaps a more traditional way of representing metadata, where you might see other data structures like, for example, trees. But this flat representation, this key value representation, really gives us two key things. Number one is it gives us a flat mapping space, right? Keys values is a very flat mapping space as opposed to a tree, which forms more of a hierarchical structure. That flat mapping space, it turns out to be have provided a lot of desirable qualities in terms of how to split it up. If you think about a tree or a graph, it's just very hard to split that up cleanly, very hard to partition that up without introducing a lot of coordination. And that ends up being a barrier to parallelization. Number two is by flattening the representation of all the data and metadata in the system into this key value store, this also gives us a representation that packs very well and lays out very nicely on Flash. If you think about it with the key value store, we can very easily build out a journaled style or append-only style set of data structures that are both very well suited to the append-only nature of Flash, but they also don't require a lot of complex background management. Right, and the reason why that's desirable is twofold. Again, it comes back to our ability to parallelize the work in the system, whether it's managing front-end customer I/O, right, application I/O, or the background work in the system. By simplifying the background work in the system, we can A, ensure a greater degree of scale of performance, and B, we can provide a much more predictable performance envelope to customers, right? If you think about it, if there's a lot of unpredictable and bursty background work, that's eventually going to affect your foreground or application performance. And by simplifying the representation of our metadata, that gives us A, an ability to parallelize it, and B, a way to just simplify the background management to where it won't interfere at all with a foreground performance. And so, perhaps going back to the database comparison, this is, similar in concept, right? To if you look at parallel databases, it's similar in concept to how, a large database will be broken up into flat table schemas, right? You'll kind of break up your data into individual tables. And then the database engine itself will break up and parallelize operations on those tables even further as it needs to scale out. And that's essentially the approach that we've taken as we've built the core of the FlashBlade engine. So, the second step in being able to exploit this parallelism is, that the key value representation provides us is, to essentially is essentially to assign ownership of individual parts of the metadata space to different what we call virtual controllers, right? If you think about it, the key value representation gives us a way to split the namespace and split the metadata space into different chunks that we can now parallelize and assign to different compute units within the system. We don't want to assign those, we don't want to assign the ownership of portions of the metadata to individual compute units by, CPU ID. We don't want to say, hey, this part of the system is managed by this blade in particular. What we want to do instead is create a concept of a virtual controller. We want to say, hey, look, if we split the work of the system into 100 different pieces, I want to be able to stand up 100 different virtual controllers. Each of those virtual controllers could run on any of the blades in the system at any point in time. But now those virtual controllers are able to manage a portion of the logical address space. They're able to manage access to and control of a portion of the metadata space, so file names, directories, changes in the namespace. They're able to manage a portion of the physical storage space, whether that's data access, data layout, garbage collection, flash management. But most importantly, they're able to manage all of those things independently, right? They can do all of that work, whether it's foreground, data access, whether it's background data management like GC and flash management. They're able to do it all without coordinating with other virtual controllers. They can do it independently, and that's really the secret to unlocking linear and predictable scale is being able to break up the problem into smaller pieces and then parallelize the processing of those pieces. And so we do this by assigning ownership to these virtual controllers and then providing the ability for these virtual controllers to run on any of the blades in the system. Right? We wanted to introduce this layer of virtualization because again, if you break up if you assign ownership of and management of a part of the system to a particular compute blade, you've now created an availability issue. You've also made it harder to scale, right? What do you do when you add more blades in the system? How do you get those compute cores to work? We solve this problem by essentially creating this virtualization layer that says, hey, as I add more compute blades to the system, I'm just going to redistribute these virtual controllers and run some of these virtual controllers on these new blades. I can put those cores to work. And so then the last piece of the puzzle here is, okay, great, we have an efficient representation of our metadata that allows us to split the work up and break the problem into smaller pieces. We have a way to parallelize the work of these smaller pieces across a great many of compute cores. That all sounds well and good, but how do you do things like maintain the POSIX namespace rules, right? If I rename a file, that's got to be coordinated. So how do I ensure that when I rename a file, it definitely doesn't, it definitely leaves its old name and definitely gets its new name. And so the last piece of the puzzle is tying together the coordination that you do eventually need to manage. And so for this, we go back to the database community and we borrow another concept, which is this idea of distributed transaction management, right? And the idea here is that we need a mechanism, we need a highly optimized engine to coordinate very tight changes between these virtual controllers as they're working with the namespace, working with the file system rules, for example, to make sure that the changes that each part of the namespace are undergoing are happening consistently. And so the way we do this is really, again, borrowing the ideas of distributed transaction engine. It's really an optimization on a two-phase commit protocol. And the idea here is that the virtual controllers can each essentially stage the changes that they need to make. So for example, we use the rename example of a file. You might have a couple different parts of the namespace involved in that. You've got the directory, which has a name link to a file inode. You've got the file inode itself. You might have some other parties in that transaction. You might have a different directory that's the file's being moved to. How do you coordinate, how does the virtual controller that manages that directory coordinate unlinking that name from the file with the change of the file inode itself to represent the change to the modification time? How do you coordinate that with the target directory? Right. And so the way that we do this is provide a mechanism for essentially each of these virtual controllers to stage their changes and then kick it to this distributed transaction engine to commit those changes in a way that doesn't conflict with one another. And so we've done a lot of work, and we can probably do a whole separate in-depth dive on the inner workings of this transaction manager. But at a high level, we've done a lot of work to essentially highly optimize that and to do it in a very opportunistic model, which is without introducing distributed locking. And so what you get then when you piece these three pieces together is you've got the core of our metadata engine. It looks a lot like a distributed database with very flat schema-like style design, an ability to partition and break up a lot of the work in the system, whether it's front-end I/O, whether it's management of the metadata, whether it's the namespace. And we have a very optimized transaction engine to ensure that all of the consistency rules, the transactionality, the POSIX rules, for example, get maintained as we split the problem up and piece it all back together. So, I know that's a lot of information there on this one slide. I'm going to pause there and see any questions on this.
I come from an orthogonal. I'm mainly into networking, as in the IT infrastructure space. And the challenge that I have with storage nerds is that they're also detail focused. That the thing I like about what you're talking about today is that you're actually customer centric instead of arguing over the shape of the bits and whether they're green or blue or something, right? Are customers responding? This is a fairly broad question. Are customers responding to this approach? So instead of haggling over blocks versus, Ceph versus whatever it is that's the latest fashion in storage land, block or file or scale out or scale in or scale up, are customers responding to this near enough is good enough type of approach that Nutanix is espousing? What
I'd say is, relative to what I just walked you guys through in terms of the architectural underpinnings, customers are definitely responding to the outcomes that this approach can deliver, right? And I would highlight two, but Matt and Rajiv might have others to chime in on. Number one is all of the attributes of the engine I just walked you through are what allow us to deliver very predictable and linear scale as we add to the system, right? If we think about a customer that started with us at 7 blades and has grown to 150 blades over time, a 20x increase, all of the database mechanisms I just walked you through, that's what allows us to put those cores to use in a very predictable, linear kind of scale of performance as they grow the system, right? It's actually not that hard to network computers together, right? And it's not that hard to build more computers and tie them together. What's traditionally been hard in file systems is making sure that as you add more cores to the system, as you add more DRAM, for example, as you add more processing power, that you can actually put those resources to good use, as opposed to lose all of those benefits to coordination overhead. And that's one outcome that customers really gravitate towards, the ability to say very almost do a spreadsheet exercise and say, hey, look, if I need twice the IOPS, I know I can add 7 more blades and I'm going to get that, right? Oh, I need 20% bump in throughput. Okay, I can add 1 more blade, I'm going to get that. The second attribute and outcome that customers are really gravitating towards, driven by this design, is this is really what is critical for us to delivering on a variety of small file, large file metadata performance. Yeah. Well, why is that, right? It quite simply, historically with scale out distributed database systems, scale out or distributed file systems or storage systems, there's always been a coordination tax. There's always been a kind of a little bit of a fixed cost of managing the distributed access, the distributed management.
Yeah.
And when you're dealing with large file access, you're streaming, a 500 gigabyte file, you can amortize that cost. You're not even gonna notice it, right? If you're doing that, however, in concert with, in combination with accessing 100 byte metadata files and notification files and triggers and doing a tremendous amount of metadata access, that's where that overhead really kicks in and hurts you, right?
Yeah.
And so our ability to do all the things I just laid out is really what drives that.
Yeah, like this, what you've done here parallels what startups have done for the last decade or so. So it's not an innovation as such. It's definitely following the market light trend, which is great because you guys have managed to packetize it in product and sell it to customers and convince customers that your flavor of chocolate's better than other people's chocolate, right? Which is fine. I guess the second thing I wanted to ask is, I'm still seeing people say that when they deploy this solution, that the networking doesn't work. They have troubles running the storage clusters shared with other networks, that these systems or the support mechanisms or the operation, somewhere along the line, it all breaks down. Do you have, is that a valid statement? Do you find customers struggle to make the networking work for your distributed storage, or do you just run on any storage under any circumstance?
I would say that's not something we see, and that's because the vast majority of the networking in the system is internal to the system. It's within the surface area of the product. I would say, in full disclosure, I would say the two areas where we do work with customers through kind of network integration. One is configuration of essentially lags or MLAGs or LACP groups across the port channels into the system. And then I would say in the earlier days, but less so these days, we had some customers that had network segmentation requirements between management networks and data networks, and kind of working through the ergonomics of that. But I would consider that the periphery. The vast majority of the hard networking problems are internal to the product, and that's really not something we field a lot of.
That's true, because Nutanix, you specify the servers and the switches that connect them together. In that sense. Yeah, I can't go and connect your product on my servers or a switch that I got from somewhere. I have to use your hardware.
Not really.
Well, it has to be hardware you've blessed, right? It has to be hardware that you've taken to the high priest of validation and said, you sprinkled holy water on it and said it's certified for use.
Yeah, no, I mean, so I guess we take a very binary view of this, right? So you can't take your servers, you can't take your servers and plug directly into the layer that I'm showing here, right? You can't take your servers and directly talk to individual blades, and that's by design. But you can take your servers and any kind of stock, standard networking switch and plug into the outer surface area of our product. And whether that's in a single chassis design, that's the integrated network within the chassis, in a multi-chassis configuration, whether it's our external fabric modules, but those speak into a completely standard, basically a very completely standard layer 2 integration, right? All right. So moving ahead, just glancing at the clock, I'm running far behind. So, we spent quite a bit of time talking about the core database engine, and that was by design. That really is the driver of so much of what we do. So what does this get us, right? And what else does it fit in? Well, number one, it allows us to distribute everything very evenly, control the system into lots of different compute cores, and minimize the cost of doing that. It also gives us a very nice way to optimize our data layouts without trading away efficiency. And this is something that historically, other scale-out systems have had to trade away. With our key value store, we can, borrow a lot of the same techniques that we use in FlashArray, our block product, to use, for example, variable length encodings and things of that nature to be very efficient about how we optimize for small as well as large file or object sizes. And then number three, it provides us a very nice building block to start, working with the flash and the layer below us at a very, very tightly integrated level to drive a lot of the parallelism that we have with the compute layer all the way down into the flash. And so if we dive down into the next layer down, right, into that flash layer and look at what are some of the things we want to get out of the media, right off the bat, what I'd say is we want to optimize for as much parallelism as we can expose, all the way, from the kind of that parallel database engine I just walked you guys through, all the way down into the flash chips as much as possible. All right, we want to do this for a couple of reasons. Performance, should be obvious as kind of number one. Density and scale is another reason, right? If we want to, over time, increase the amount of flash that we're driving in each of our devices, each of our drives by, call it order 5x or 10x, we recognized early on we weren't going to be able to get there, if we had to scale up all of the in-drive kind of translation, machinery, and machinations that are happening there. Number three is we also wanted to unlock that interface so that we would be well positioned to work with future media, right? We know that each generation of solid state media becomes, shall we say, more and more challenging to work with. And so, we recognized early on that we would need a path to be able to move more and more of that visibility and processing open up to a higher layer of software to where we can make better, and more efficient decisions. And so, net, we did this by really just taking a look at what's in SSD, right, and stripping everything out of the way that we don't absolutely need. And that really was the genesis for what became, direct flash. This started in FlashBlade in 2013, 2014, this technology, but you now see it across all of the Pure portfolio as direct flash. And again, the idea here really is to optimize the path to flash, get everything else out of the way, access it through a very high concurrency protocol, NVMe with vendor-specific extensions. And being able to do that, move everything you can outside of the path to flash and hoist it up to a higher layer of software where you can make better system level decisions. So, this is a path that we really embarked on, driven by performance. This is really what led us down this path. But, if we look back on it, what we got out of this was certainly the performance, but we also got much better reliability, efficiency, and a path to density. And those things are really important. I want to spend a couple slides kind of diving into each of those points because in many ways, they've really become just as important as performance, in kind of how we look at direct flash and how it integrates into our products and product families. This is a bit of a math chart, but what I'm showing here is, really taking a look at reliability and endurance first. One of the biggest effects that we get from, well, I would say our entire stack, but enhanced by direct flash, is our ability to reduce write amplification in the system. As you know, write amplification is for every byte of data that a customer or an application writes, how many additional writes does the media undergo through either transformation or garbage collection or just having to deal with the append-only nature of it. And so, if we take a look at the graph on the left, what this is showing is that with just the Purity software, right, the metadata representation, the way that we manage that metadata, the way that we garbage collect the data, the way that we pack customer data, we're able to reduce write amplification by about 3 to 4x, as compared to your typical SSD usage. That's great. You add direct flash into the mix, which is the ability to have visibility and direct control down to the flash chip layer, and we can get about a 3x improvement upon that. And so you kind of combine those two, and you're looking at about a 10x reduction in write amplification, as compared to your typical SSD usage. That's really, really important, as you know, in terms of how it extends, extends lifetimes, drives better endurance, through simply preserving PE cycles by not having all that write amplification. The second thing this drives is much better reliability, right? Now, part of that comes from the endurance improvements we get by reducing write amp, but a lot of this also has to do with the enhanced visibility we have all the way down to the flash, right? If you think about it, if every IO that we issue down to our devices, our drives, can return back fine-grained telemetry on the health of that page or that block that we're reading or writing to, that enables our system software to make far better decisions as far as how to use the flash, how to lay out future operations. If a certain block or an area of flash needs to be rewritten, how do we avoid doing that at the physical layer, but rather combine that with a logical GC? How do we kind of get a 2-for-1, right? There's a lot that goes into that, but what comes out of it is a significant reduction in what we track, which as annual return rates, right? So this is a good proxy for essentially dry failures. So if you look at the industry average, right, you'll see again the improvements throughout in purity, just by reducing write amplification and and just knowing how to treat the flash well and knowing what's happening within that flash layer drives a significant reduction in that failure rate or that return rate. You add direct flash into the mix, and that drops it by more than 50% on top of that, right? So significant improvement in reliability, reduction in failure rates. The other thing to point out here is that it gets better in time, right? The ability for us to get fine-grained telemetry and feedback from how we're using the flash means that our job isn't done when we ship that first drive or that first software release. We can continually improve that, right? And we have. And so what the two bars in orange, or the two sets of orange bars, are showing are for a cohort of in the middle SSDs or DFMs, for a cohort that we've shipped at kind of the beginning of that shipment cycle versus a couple years in, how has that failure rate or that return rate teed down over time? And that's a good representation of the continued improvement in reliability we're able to drive out of the system. Again, completely unlocked by our direct flash technology, our ability to have fine-grained visibility and control over how we're using the flash down to essentially the individual cell level. So the other significant advantage that we get through direct flash beyond performance and reliability and endurance is path to efficiency. And we measure efficiency in a number of ways, but the two, I would say that the two most impactful that I've called out here are measured both in terms of cost as well as power efficiency, right? So I'm showing kind of two graphs here, and I'll start off with the one on the left. But both of these graphs, I'll start off by saying, are based on our internal models and projections. So these are very much the models that we use to guide our product development efforts and everything that we project internally. The graph on the left is showing the cost efficiency benefits, the one on the right showing power efficiency benefits, and how we see those trending over time and contemplating future roadmap and kind of development activities. And so, if we start off by looking at the graph on the left, what we're showing here, what we're looking at is the cost per usable space, in what we've modeled as an SSD versus an HDD-based system, and how those converge over time. And what we've really done here is looked at, a typical kind of competitive type of architecture and costed that out, right? And looked at how do these things converge. The two main drivers here, really, the first should be of no surprise is the cost curve and decline of media, right? As flash declines in cost faster than disk, you see the SSD-based arrays coming down in cost. The other driver is a little bit less apparent, and that's really what gives us a tremendous advantage over what we would look at as the competitive set with direct flash. And that second driver is density, right? The denser the systems that we can build, the more of the cost we can move into the media, the more efficient of total system cost we can deliver, right? So said another way, if we can build far denser systems than the competition, to ship a petabyte of storage, I have to ship far fewer Intel processors, I have to ship far less DRAM, I have to ship far fewer chassis, far fewer networking cards, far fewer everything around the storage. And as the cost of the media declines, those non-media costs start to dominate the system. And so by driving density higher, we can shift this curve down and to the left. And so if you look at our efficiency projections, what you'll see is that our advantage with direct flash has us bringing in that total system cost cutover point quite a bit sooner than what we see across the industry. You're also seeing two lines here, right? You see the solid line and you see the dotted line. What the dotted line represents is, even, or I guess it's dashed, even denser systems that we would contemplate building in the future, right? And so again, the takeaway point here is that direct flash is really giving us a path to control our own density destiny. Well, that's a tongue twister. And that density drives efficiency. It drives efficiency in cost. It also drives efficiency in power, which you see on the right-hand side, right? And again, this is, maybe another way of looking at the same effect, which is, if I can put more flash effectively behind the same set of controllers, the same set of CPUs and compute complex, if I can deliver more effective capacity, then the effective power utilization per terabyte has gone down, or the number of terabytes or petabytes I can serve within a given power envelope has gone up. And what we project is, though today we've got about a 50 to 60% advantage over competitive flash offerings, what we project is that gap will increase to 3x or 4x into the future. And again, a lot of that is driven by direct flash and the efficiencies and density that we can drive from that. So any questions on direct flash before we move on? All right. So, we've talked a lot about flash and how we use it. It's the bulk of our system, but we also have put a great deal of focus and effort around being efficient about how we augment that flash with other solid state media, right? Like many systems, we have some higher speed way to ingest and land data before it ultimately lands on flash. In our system, we use NVRAM, but a lot of systems have some other media besides the long-term storage media, to provide that ingest capability. One of the critical insights and decision points that we undertook from day one, right, was to look at our high-speed media, NVRAM in our case, as only a write buffer, right? We do not read from it. We only use it as a landing buffer for staging writes that are coming into the system before they land on flash. Well, why is that? All right. Well, that critical decision leads us down a path of not relying on that media for access efficiency. Because we don't read from it, because it's just a write buffer, we don't depend on it for providing access efficiency. We don't have to pin our metadata structures in it, in that high-speed media to get the performance out of it. It forces us down a path of designing more efficient metadata structures, efficient in both storage, because we're going to keep them on flash, but efficient in access as well. Couple that with intelligent access methods, right? Ways to index into that metadata and cache it in DRAM in the processing engine in a stateless tier, but be able to derive the performance through those means without having to rely on the high-speed media. Well, why is this so important? Because it sounds a lot more complicated, right? It sounds like it is a lot more work, and it is. But it's important because it drives two very important benefits, right? Number one is, because we don't rely on this additional high-speed media, whether it's NVRAM, whether it's storage class memory, because we don't rely on it to store our metadata structures, it allows us to decouple the scaling of the elements of our system. We can grow flash with density and capacity needs, and then we can size our NVRAM simply for performance. We don't have to grow those things in lockstep. And that becomes really important because if you look at the growth vectors and trends that we see, we see denser and denser systems. We see the need for higher and higher capacities in customer environments. And we see a cost curve that's driving the cost of flash media lower and lower, right? And so what you want to do is center all of your scaling in that low cost media and augment it and size your high performance media only for the performance needs. And that's essentially what this design allows us to do. But to do that, you have to remove the hard requirement. You have to remove this idea that you've built a software architecture, a set of metadata structures, a processing engine, all built around this idea of metadata pinned into high-speed access media. Because once you've done that, that locks you down, that locks you, into a path that's really, really hard to get off of. And so we recognized this fairly early on, and essentially chose our path. We chose to do the hard engineering work up front, build the data structures that I walked you through, build the transaction engine, the processing engine, the parallelization engine on flash-based structures and media, using only our NVRAM for write buffer. And that gives us the ability, and has, as we've gone through the last, kind of 5-6 years, that's allowed us to grow, our density and capacities independently of how we grow that layer. And as we look into the future, that becomes even more and more important. So a tremendous scaling advantage you get. You also get increased reliability, right? The ability to, if you are representing your data and metadata in 2 different places, you've now got to solve fault tolerance, you've got to solve availability, you've got to solve all these problems twice, right? These are hard problems, right? As a customer, you should be, I should say, wary of vendors who are trying to take a hard problem and solve it twice. What we've done is essentially collapse that into one, right? By storing everything on flash, we can centralize the management of those hard problems, solve them once, drive higher reliability, and ultimately you combine these things and you get better economics, right? And that's, at the end of the day, what a lot of customers, see out of this. So, I'll pause there because there was a lot that I just walked through in terms of direct flash, in terms of how we manage the flash elements and the non-flash elements. Any questions coming out of this?
Yes, I'd really be interested in seeing what everyone thinks, because we're obviously making claims. Rob is obviously making claims about FlashBlade versus the competition. So, do you all agree? Do you all agree with what's been said so far? You happy with that? Are you happy to, stand by it if you go and talk to any of the pure competitors? To say nothing is to agree, by the way, guys. So, okay. All right. Well, Rob, it seems that you've got everyone's agreement on that one.
Excellent. Well, that's a great way to move into, not only would we agree, apparently you guys would agree as well, our customers agree, most importantly, right? The efficiency I just walked you through, it pays off for customers of all sizes. I would say we're particularly proud when we can support kind of the extreme ends of the performance spectrum. This is another example from a customer. This is a flagship financial institution, a quant trading firm, among other things. And they're running, several, I would say, very large scale workloads, but very disparate workloads on FlashBlade, a highly concurrent set of simulations, Monte Carlo simulations that they're running across a, platform of thousands of servers, tens of thousands of cores, reading, writing, very mixed access, a lot of the access patterns and demands that we just talked through. And because of all of the elements that we've just kind of covered off on, whether it's the platform layer, whether it's the core processing layer, they're able to, get access to this, tremendous amount of performance, but, more importantly, deliver a very simple end user experience, right? This is something that Rajiv started us off talking about, which is, how do we balance the need for a tremendous amount of performance with the fact that, at the end of the day, the end users in this customer aren't storage experts, they're not even IT experts, they're quant traders, right? And so this is a great example of how it all comes together, for those customers. So the platform layer, we've already talked a lot about this. Direct flash was kind of the, I would say, the lion's share. I would say just a couple thoughts. We know that, as we look to the platform layer and the demands of scale, right? We know that we have a wide range, very wide spectrum we want to scale to, whether it's capacity, whether it's namespace size and complexity, or whether it's the compute demands on the system. But more importantly, and really the trick is to be able to do it in a way that allows customers to start on the small end of that spectrum and continuously grow all the way to the largest end of the spectrum. And so just a quick visual of how this looks and how we do this. What you see on the left column here is the smallest configuration of FlashBlade. So this is less than half of a chassis, 7 blades with a small blade configuration, all the way to the maximum configuration, 150 blades of 52 terabytes, so about 3x the size. And on the right-hand side, what you can see is what this actually looks like in a production environment. And you can see, we actually had a slide very, very early on in FlashBlade that looked at cable count per petabyte. And what you can see here is a very, very tight and very simple, which at the end of the day drives reliability configuration. And so, this is not just theoretical. This is an example of a customer. This is a small technology, actually not that small anymore. A technology company in Asia that has grown with us, since 2017, as they've built out what has now become a fairly large-scale AI and ML environment and infrastructure. So they started with us at almost, kind of the smallest configuration, 9 by 17 blades. Over time, they expanded that system by adding more blades, giving them, a third more that performance and capacity. They upgraded those blades to the 52 terabyte blades. They expanded that system to fill out the first chassis. They added a second chassis, and now they're onto their third chassis. They've gone through, a number of software releases throughout the years, 6 different expansions, moving from one blade type to another. But most importantly, they've done this all online, right? This has all been non-disruptive, getting back to our focus on delivering on the Evergreen promise, the idea that, we're going to help customers transition and evolve through, their expansion journey. And this has all been, and this is all been, performed very fluidly without any sort of reconfiguration, any sort of redesign of their application stack, right? They've been simply able to add performance capacity as they've needed throughout the years. A couple last customer examples to close out. We've mentioned a couple different, I'd say verticals or workload sets. We talked a lot about rapid restore. We've talked about AI ML. We've talked about chip design. Another area of technical computing that we've been very successful in has been life sciences. And so these are a number of customers in the life sciences industry doing, whether it's genomics, either primary or secondary analysis, whether it's research and AI modeling, model training on genomic data. But what you can see here is, and getting back to one of the questions earlier, which is, we can talk about the architecture and the bits and bytes all we want, but what really resonates with customers? I think this slide says it all. What resonates with customers is significant reductions in time to result. Right, whether it's 9x reduction, you see 24, 26x reduction. These are results that at the end of the day, this is what life science researchers are striving for. We see similar reductions in time to result in AI model training and chip design, fluid dynamics, really across the board, right? And at the end of the day, that's what customers really care about. And then the last customer example I'll end on before we turn this over.
Robert, a question on that other chart.
Sure.
It's really hard to make any comment about a competitor. Can you characterize the competitor? I know you can't state who they are, probably, but could you characterize what is the competitor environment? What are you comparing yourself to?
So in each of these cases, you're asking about the gray bar?
Yeah.
Yeah, so in each of these cases, the gray bar is what the customer told us, either their existing system we were replacing or competitive systems that they were evaluating was performing at, if that makes sense. So
this probably wasn't just a pure bake-off of 2 like systems, particularly the older system. Okay, thank you.
It's pretty rare that we ever get into a pure bake-off of 2 like systems. Because at this kind of inflection point where you have like modernization happening, on the block side of the world, excuse me, back in 2012, et cetera, there were, we were competing mostly against hybrids. So there, the competition would be either traditional spinning disk or hybrid arrays. Eventually, there were a couple of other all-flash arrays. Violin was obviously in very early in this space, but Violin was taking a much different approach with essentially fast storage with no data services. We were blazingly fast storage with no data services. We were providing very fast storage with lots of data services. There's a similar thing in this market where our competition in most of these opportunities is still against some form of disk. So it's rarely apples to apples.
Yeah, so I wouldn't call this a validation. I mean, it is a validation, but it's like not a competitive bake-off. It's more of a comparison of before and after look, almost. That's
yeah, it's the best. It's the best position to be in, right? Because
yeah.
When none of your competitors have what you have, and you're showing 7x improvements on genomics research modeling. That's why our win rates are so high, right? It's when it's kind of that dream scenario for our salespeople, right? Because when they're in an opportunity, they know they're going to win because there just aren't the competition is just not there. And where the all flash, where the competitors do have all flash arrays, either the customer support experience has been so poor with them, for several years that, moving to, their newer platform based on old architecture is less interesting. And the startups in the space are, relatively small companies, and they're not betting, huge enterprise production workloads. So it's a pretty nice spot to be in.
All right. So to close this off on kind of customer examples, I wanted to also touch upon, a recent announcement that Facebook or Meta provided, which was, kind of, I would say, letting the world in on the fact that we've been working with them for over 5 years and kind of building one of their largest, what they've now described as their world's largest AI research supercomputer. And this is, this has been a partnership that, I've been involved in. A lot of early engineers and key engineers on the FlashBlade team have been involved with since the early days. And this has grown now to an environment that is, really cutting across all of Pure's product lines, whether it's FlashBlade, as well as FlashArray//C. And what we're doing here, is really powering all ends of, Meta's AI research supercluster, whether it's their production model training environment, as well as their, I would say, more ad hoc or research-oriented environments. And we're doing this with a combination of FlashBlade as well as FlashArray//C. At the end of the day, we can kind of, we can, peel back the cover and kind of the layers of the onion as to what led Facebook or Meta to select FlashBlade initially, and then the entire Pure portfolio for this environment. And there's elements in there about, everything you would expect, right? Performance certainly was a key consideration. The combined price performance, that combination. Scale, the ability to handle the tremendous amount of data we're talking about. We're at about 170, 180 petabytes today, and they've indicated this is growing potentially to an exabyting scale, right? So a tremendous amount of data. But the two key elements which are less, I would say, appreciated about the Meta environment and why they selected Pure is, at that scale, a number of other demands come in, right? And those bring us back to a lot of the key technologies. The density that we're able to provide gives them footprint and power reductions and savings that become very, very meaningful. There were parts of this environment where, the Pure technology driven by direct flash was really their only way to be able to meet the needs that they had in terms of capacity and performance within their existing data center and power envelopes, right? Without having to extend, build out new data centers. And then the last point I'll kind of close off on is just coming back to the simplicity end of things, right? These are live production environments that are running, not only supporting, thousands, tens of thousands of employees and engineers, but they're supporting production services. And so at that scale, if you think about exabyte scale, at that scale, it becomes even that much more important to have building blocks that are bulletproof, are reliable, are simple. And that's, at the end of the day, that combination of price, performance, density, power footprint savings, and simplicity and reliability. Those are all things that drove Meta to select Pure. And those are all things that Pure's been about since day one, and we're really dedicated to delivering to all of our customers. And so, with that, I'll stop the share.
Well, Rob, just before you do that, one of the things on the Meta situation is, all of these transitions, everyone say, okay, well, how many Metas are there going to be in the world? The reality is there may not be as many Metas in the world as there are cans of Coke, but derivatives of what Meta is doing is what will become this type of standardization of architecture for this type of compute. And the problems inherent to that situation won't change. Performance per watt and performance density is going to matter. I know that I know that it's not ultra interesting to talk about saving floor tile space in data centers, et cetera, et cetera, et cetera. But saving power and floor tile space in data centers is very interesting to customers. And when you look at that Meta example, right, they have empty space in their data center, not because they can't fill it. They could fill it. They don't have the power. So that sort of density of power and processing power per RU becomes pretty important.
I think that's very well said. And I think a better put than I was trying to wrap it up. So, with that, we've thrown a lot of information at you guys, very, very dense. Hopefully this has kind of hit the mark as far as, as far as diving into the technology and the underpinnings. Like Matt said, and I think we had a question early on, I think a lot of the focus that we have put into FlashBlade, a lot of the focus that we continue to put as we develop and innovate is more so on the architecture, the design and the underpinnings, and designing for the future than any individual feature, which is not to say that we don't care about the features. We do, but we put a lot of effort and thought into not just designing the feature in front of us, but really paving the path for kind of what's coming around the bend.